Thanks, everybody, for joining this session. I'd like to take the time today to present something that SAE International has been working on that has been really a problem confronting the engineering field for quite a while, particularly in the industries that SAE serves, which is the aerospace and automotive industries. And it's really surrounding engineering specifications or engineering industry standards. And so what SAE has done is we have addressed some of this with some AI models and machine learning approaches, which is what the topic of today's discussion will be. So as Monica mentioned, I'm with SAE International on the product development side of the business, and Dr. Nyberg is with Carnegie Mellon University as well as Cognistx. A lot of the information that we're going to share today can be found in a white paper entitled Digital Standard Systems, an Integrated Approach to Engineering Standards Usage, which is a free white paper that can be found at sae.org. So I'm going to start off with a little bit of a background on what the problem is that has been plaguing the aerospace and automotive industries for quite a while. Industry standards have been around for hundreds of years. 100 years SAE has been around for, and so it's been a problem since then. The real problem has to do with complex supply chains and data exchange and sharing of information across the supply chains. So there's this supply chain dilemma, and engineers and management operations, particularly in aerospace, where we have these very complex supply chains that are dependent on documents. The question for them is, how do I access this information? You know, they got millions of documents that are used within the development, maintenance, production of an aircraft, and how do they access that information across the documents in an interoperable format without having to task their staff, particularly because those documents change over time fairly regularly. And so that became, because SAE is one of many providers of industry standards, that became an SAE International dilemma, where we had to understand, how do we bulk convert thousands upon thousands of documents that we provide to the aerospace and automotive industries? How do we bulk convert those, particularly when the documents are actively being used and they're being cited by regulatory bodies around the world? How do we do that? And how do we do that in an automated fashion so that information can be accessed interoperably and connected to our users' internal systems so that they can have a broader system integration, and also improve things along the lines of change management? So how do I manage, as this data is changing, how do I manage my my internal systems? So I always never want to assume that everybody understands the standards or industry standards. So for a little bit of background, I wanted to just give you two examples of documents that we had to look at. How do we automatically extract? How do we train models to automatically extract and structure information within these documents? We knew we would be using some type of NLP, but the documents are so varied and there's so many of them. How do you possibly train a model given that situation? And so we've got two types of standards. One is that we focused on, although we have many other types of standards. But we looked at material standards. So this would be any kind of actual material that is used in production or in development of different parts and components. And that's a material standard called an aerospace material specification in this case. And then we have part standards, which go into design of parts. And so these standards are developed by hundreds of committees around the world on an ongoing basis, and these are updated constantly. So one of the things that we were faced with is it's a lot of approaches, and we had to look at the documents and say, okay, which one are data centric and which one are document centric, and specifically which ones are very, very heavy in textual data that we're trying to extract and make sense of, and which one of these are very much more complex on the numerical data side, as far as tabular data and data that's housed within images. And it really was a complete mix. So to give you an idea of some of the things that we had to extract and that we had asked our partner Cognistx to help us with, here's an example of tabular data. So you can see in front of you, there's two very different types of tables. These are two very simple representations, I'll add, of our tables. Typically, the tables within these documents are really varied, multiple headers, multiple different types of column configurations. And so it can be quite difficult to come up with one model to be able to identify what type of table is being used in a particular case. An example of requirements data, this is much more textual heavy, but you can see there's this has to do with sentence extraction. So sentence identification and sentence extraction and categorization. And it's not always, you're not able to do it necessarily in a rule-based manner, which is why we had to use ML, because there are no specific rules necessarily that we can use in this case. But the two boxes delineate two different requirements, and those are things that we would be looking to extract and allow our users access to. So some of the background of the system and why we have had to do what we have to do. This is the on the left-hand side, you'll see an example of just a schematic of the aerospace product lifecycle. So very similar to those of you who might be in product development. There's a design, develop, test, release cycle, and then obviously aerospace has a huge maintenance piece at the end. And at every part of this entire process, there are a multitude of computer-aided engineering tools. There are specific backend systems that are used that are in-house and specific to a particular OEM, a major or minor component manufacturer. And different types of documentation systems. And these have to be monitored and auditable per regulatory guidance. So it becomes a very complex situation because things are being passed around the supply chain, and then you want to maintain data integrity and also make sure that you're connecting to the primary data source. So what we did is we bulk converted a lot of, or most of our documents to allow for it to be then structured, and then an API built on top of that or connected to that database so that it can be directly connected to these engineering tools. So the database and API piece is fairly straightforward. The tough part was actually being able to pull that information out of the documents. So we did come up with a patented methodology and AI models to do this. And the first step really was pretty straightforward, although it wasn't straightforward in developing the model, but it was the automated extraction. We extracted sections of the documents. We extracted the tables from the documents. We also extracted all of the data points within those tables. And then we categorized the different sentences into what we'll call, what are requirements. And then we categorized the tables, and then we categorized the data within the tables. So we came up with a extensive, fairly comprehensive data model out of this. But it's one of the questions that I think was posed in the last session for Cheng-Shi was related to the variability of the data and what pre-processing is necessary. So there was a lot of normalization that we had to do before we did any kind of machine learning. And so that is where a lot of the SME sat in the pre-processing of that data. Not so much for materials, but for parts. What we noticed in engineering specifications around the world, you'll notice is that the variables that are cited within drawings are not normalized. And so you might have different organizations and different industry bodies calling a particular dimension something different. And so it's difficult to identify where things are because the cues are not there. So we had to work on normalizing that data, particularly for drawing data. And then we were able to do the supervised machine learning. And so one of the things that we built in was, because we were going through so many documents, that these algorithms should be able to be applied to documents that are not developed by SAE in documents. So we have started to test these algorithms on documents not owned by SAE within aerospace companies and parts of the supply chain, and they've been fairly successful. And so we have built in an iterative, as most models do, evaluation so that we can actually see the outputs. And then when we go back and we're QAing the data, we can quickly go back and retrain the models if necessary. So like anything, the whole point of this is really to have an improved data model that, or AI model that's much higher accuracy. So out of this exercise, we ended up with a web application so that people could access this data. It has really been quite profound in the effect that it will have on the aerospace supply chain. There's obviously a data model so that if customers have different data models that they use, at least they can know which fields to point to. And then we have an API that's been developed on top of that. So what you'll see is one world, that was actually not too long ago, just last year, where things were very focused on things like PDFs, change management, huge teams having to just manage document versions and updating everything within their audit trails, their document trails. Silo data, just hours of trying to find documents. We're now transitioning to a place where these customers can connect directly to the primary data source in much more interoperable formats than they have been able to before. So another example, and I'm going to pass things off to Eric Nyberg from Cognistx, and he will outline yet another example of how he's used a similar approach, but within the automotive industry to give you a different use case. So I'll hand it over to you, Eric.
Thanks, Audra. So Audra's referring to a project that was a collaboration between Caterpillar, Carnegie Mellon University, and Carnegie Group back in the 1990s, which is probably the earliest example of trying to apply this kind of normalization, both to documents and to the process of producing and using documents for technical domains. So at that time, Caterpillar had a goal of streamlining the production, translation, and dissemination of all of their heavy equipment documentation, not only for engineers, but also for mechanics and end users. And they were under a lot of pressure at that time because the European Union decided that you wouldn't be able to sell your products within the European Union unless you could provide the documentation in all 11 of the EU member languages. And Caterpillar didn't really have an effective solution for producing all of their documentation in a cost-effective way in all of those languages. So they embarked upon this effort to introduce a standard vocabulary and grammar, which we helped them to define, called Caterpillar Technical English. So the analog to the on-cue experience with SAE would be that you would start to inculcate the technical authors with some idea of how to write material specifications so that you could reduce or even eliminate these variances in what you label the columns in your tables and how you describe requirements in the text. Caterpillar not only introduced these standards for vocabulary and grammar, but they also had us build software that would ensure compliance with those standards while the documents were being produced. So an author would write their document and then they would run software over the document to make sure that it was compliant, and the software would suggest replacements for vocabulary or rewriting of particular sentences that didn't meet the standards. Caterpillar also introduced standardized vocabulary and grammar for the target languages that they wanted to deploy, French, Italian, German, and Spanish. And we also developed software to automatically translate all of the documents into those languages. This was also the time when companies first started moving away from markup languages that were only for print production to languages like SGML, which was the precursor of XML, which essentially allows you to tag for content rather than tagging for markup. This allowed Caterpillar to do two different things. They were able to achieve consistent, standardized print production, but they could also use exactly the same tagged format to deliver the information in a variety of non-printed forms. And in particular, they were very interested in making electronic copy accessible on the shop floor. Before this, a typical heavy equipment shop would have several yards of paper documents all lined up in a giant set of binders. And Caterpillar was able to replace this with something called the Service Information System, which allowed them to have essentially a touch screen in a hardened kiosk on the shop floor that would allow direct access to exactly the pieces of the documentation that the mechanic required for a particular procedure. Next slide. So once this was rolled out at Caterpillar, in addition to the sort of visionary goals that they had, they realized some practical advantages by doing this. One was that they greatly reduced printing costs because they weren't printing a lot of hard copy essentially, and because their products are revised very, very often, and there's a very large volume of paper required for each piece of heavy equipment. This was actually a significant effect. It wasn't that you were putting out one manual every year or two. There were quarterly updates to everything. And also mechanics found that by having direct access to relevant information via electronic delivery, now you could use a search engine to find exactly the section of a manual that you wanted to look at, as opposed to thumbing through a hard copy. This made a huge difference. Another big unanticipated benefit was that there was an observation that many of the Caterpillar products actually share the same subsystems or subcomponents. So, for example, the same engine is used in many different hydraulic excavators. Through the use of electronic copy, you are able to basically author pieces of the documentation one time and then share them across many other larger documents via modular reuse. And this allowed you to basically update pieces of manuals without having to reprint the entire thing, which turned out to be a huge benefit. These benefits also carried over into the translation world. In the old days, Caterpillar would have to retranslate the entire manual every time they made an update. But now they could use modular updates where they would only translate the pieces of the documents, the overall documents that had changed. But they also used the document structure that Audra referred to basically focus on retranslating down to individual sentences or paragraphs. And they were able to implement something called a translation memory, which remembered all of the prior translations of the English sentences in any given manual. And then you would only retranslate a sentence if the source English had actually changed. Otherwise, you would reuse the existing translation from the previous time that you had produced the manual. We also built automatic translation software for Caterpillar so that when there was new text to be translated, it could be automatically translated and then a draft translation presented to the human translator. And this cut down by about 80% the amount of time that it took to translate new material because the human translators were essentially making minor corrections to automatic machine translations on the new text that had been authored. And I list here in the slides the patents that were created out of this work, joint inventions with CMU and Carnegie Group. And I think what's interesting about this case study is that many of the same principles are in operation today in the OnQ system. And I think today we have even better machine learning capabilities and also interactive information capabilities, so that what we have in the OnQ system is actually a lot more sophisticated than what we delivered to Caterpillar, even though it derives from basically the same vision and the same goals. Okay, do you guys have any questions? Let's take a look in the chat. So Mike Perella is asking, Eric, do you know Eric Riebling? Yes, I do know Eric Riebling. And in fact, after working at Carnegie Group, Eric actually came to Carnegie Mellon and worked with me on several projects at CMU after working at Carnegie Group. And he and I are still good friends. Anybody else have a question?
Yeah, if anyone has a question, we can unmute you if you want to. Just feel free to speak up. Just let me know in the chat. So you must have covered everything. There are no questions. That means you did a really great job with the presentation. Wow. Thank you, thank you, thank you again. Thanks to everyone for attending the presentations all week. Please make sure to go and visit the technology showcase from 11 to 12 today. And then we will have our closing keynote at noon. So you will be able to access that through the Sched app. There is a separate registration that's required just because it's a joint session with our business as usual daily program. If you haven't attended business as usual, it happens every day. We have business leaders, we have nonprofit leaders, lots of great individuals who share their insights with us every day. So if nobody else has anything to say, we'll close the session. All right, well, thank you, everyone. Have a great day, and we'll see you at noon.
Thank you.
Thanks.
Thank you.
Thank you.
Recordings are being done. So